So, hello everyone again. This is lecture 3 part 2 of ray optics and optical instruments. In this lecture, we will continue our discussion from the last basic formula derived for curved surfaces, which was the relation between N2, N1, U, V and R. Today, we will move on with a simple example regarding this concept only, and then move on further for the derivation of Len Makers formula and Len's equation. So, I am Samir Lavankar. Let us begin our discussion. Okay. So, right now, first of all, we started with the introduction, in which we understood two different points. The first was that the speed of light is 3 into 10 to the power 8 meter per second, and the second was that the ray or the ray a beam of light always travels in a straight line. In this complete lecture series of ray optics, we are assuming a Descartes particle theory, that is, light is a discrete particle theory of light. In the second point of reflection of light by spherical mirrors, we understood first of all the two laws of reflection, that is, first is that angle of incidence I is equal to angle of reflection R, and second is that the angle of incident ray, normal ray and reflected ray always lies in the same plane. Before these two different derivations or these two different laws, we understood the definitions of what is the pole of the mirror, what is the principal axis, what is focus. Also we derived f is equal to r by 2 there. After the completion of second point, we moved on to the third point, that is refraction. So, basically what is refraction was being considered there. Then again two laws of refraction were being considered, Snell's law of refraction was being considered there, applications of refraction was being obtained there, and so on. The next was your total internal reflection. In total internal reflection, we understood the concept of how after a particular angle of incidence, the complete line or the complete what we can say light gets bend over or get internally reflected, and the complete intensity is intact. A little amount of energy is always released, or amount of intensity is always released, but at least 95% to 99% can be achieved. After that, we understood the example. So, there were two examples, one was related to prism and second was related to your optical fibers. One proper example which you can find in your surroundings also for a light pot, which is also visible, was explained in this complete concept of total internal reflection. In the last lecture, we started with the refraction at spherical mirrors and by lenses. This is basically refraction. This is refraction at spherical surfaces and by lenses. So, right now we are in this portion in which we started with the basic concepts, and by using the relations between N1, N2 and the lens and the mirror equation only, we derived the equation for the curved surfaces. So, let us move on with the discussion only. So, refraction at spherical surfaces and by lenses. Okay. So, in the last lecture we derived this equation, that is N2 by V minus N1 by U is equal to N2 minus N1 by R. Okay. So, this holds for any curved spherical surfaces. Okay. So, now let us try to implement it somewhere, and then we can understand what is happening actually. So, light from a point source in air falls on a spherical glass surface, n is equal to 1.5 and radius of curvature is given to you as 20 centimeters. So, if nothing is given to you, you can assume the value of radius equal to plus 20 centimeters here. The distance of the light source from the glass surface is 100 centimeters. That means the value of u is given to you. The value of u is given to you as minus 100 centimeters. In 99% of the cases, you will be always in negative sense only. Sometimes if you want to derive it from a virtual image, then that virtual image becomes a virtual object, and then sometimes we have to use plus sign. Okay. So, at what position the image is formed? So, basically you need to find out the value of small v here. So, basically you have everything, you have the value of u, which is equal to minus 100 centimeters, you have the value of radius, which is equal to plus 20 centimeters, and n1 is given to you. So, basically as n is 1.5 centimeters, so you can assume n1 as air is written, it is written air, therefore n1 is equal to 1, and the value, so the second glass surface is n2, which is equal to 1.5. So, hence n2 is given to you as 1.5, n1 is given to you as 1. Therefore, n21 is nothing but n2 by n1, which is equal to 1.5 by 1, which is equal to 1.5. Okay. So, now just using the equation, so 1.5 by v, so it is nothing but it is n2 by v minus n1 by u is equal to n2 minus n1 by r. So, just substituting the equation values, 1.5 by v minus n1 is 1 by minus 100 is equal to n2 minus n1, that is 1.5 minus 1 by r. What's r here? R is 20 here. Therefore, it will be 1.5 by v plus 1 by 100 is equal to 0.5 by 20. So, it will be nothing but 1.5 by v is equal to 0.5 by 20 minus 1 by 100. Multiply this by 5, multiply this by 5, this will be 1.5 by v is equal to 0.55, so gives you 2.5 minus 1 upon 100, and hence 1.5 gets cancelled. V is equal to plus 100 centimeters. What does it mean by plus 100? That means it is on the right hand side, right side direction of the this spherical surface. Okay. So, therefore, you got V is equal to plus 100 centimeters. Therefore, the image is formed at a distance of 100 centimeters from the glass surface in the direction of incident light. So, this is a typical example of the application of the formula which you just derived in the previous lecture. Okay. Let us move on with the further discussions now. So, now we are assuming the refraction by a lens. In the previous concept, we understood the refraction by a curved spherical surface. Now, we are assuming, or we are understanding the concept of refraction by a lens. Okay. So, let us move on. First of all, figure A shows the geometry of image formation by a double convex lens. So, as you can see, this is a double convex lens. The image formation, what does it mean by double convex lens? So, basically this is also a convex lens, this is also a convex lens. Okay. Image formation, the image formation can be seen in terms of two steps. So, first of all, what will happen is the first refracting surface forms the image I1 of the object O. As you can see, this is the image I1 of the object O formed by this surface. Next is the image I1 acts as a virtual object for the second surface that forms the image at I. So, this is the typical sequence which I said that 99% of the time you will use the value of u as minus 100 only, but this time you will use the value of u as plus 100. Why? Because the direction of the incidence of light is in the same direction as the measurement of the image O, which is here the virtual object O. That is fine. So, the image I1 acts as a virtual object for the second surface that forms the image at I. So, as you can see, this forms the image at I. Figure C. So, this is the typical explanation for figure C here for you. Next is, so first of all, let us complete this sequence, and after the sequence complete, we can move on to the second refracting surface. Okay. Just I will try to go very slowly now. So, now first of all, we are trying to implement the mirror equation here, the refraction equation here. So, applying equation to the first interface ABC, we get, so N1 by OB, so N1 by OB plus N2 by BI1, N2 by BI1 gives you N2 minus N1 upon BC1, quite evident. Okay. So, now what is the new thing here? So, a similar procedure is applied to the second interface ADC. So, now you are applying this for ADC now. So, for ADC what will happen is nothing but DI1, so basically this value of equation. So, this is di1. So, this will be here interchange to the value plus here. So, it is nothing but minus n2 by di1 plus n1 by di. So, n1 by di, because this is in the same sequence here, equal to n2 minus n1 by dc2. dc2 is in this direction. Okay. And because the direction is positive only, therefore, this will be positive only. Okay. Now, for the thin lens, so what is happening for the thin lens? Basically, that is BI1, this BI1 is equal to DI1. What is DI1 here? This is DI1, because we are assuming that these two portions are very near to each other. So, basically, even if B is formed here in this sequence here, and this B and D are very close to each other. Okay. So, this thing is also been explained. Now, just for a thin lens, BI1 is equal to DI1. So, adding above two equations we get. So, just equations adding. So, let me just add the above two equations. So, it is N1 by OB plus N2 by BI1 is equal to N2 minus N1 by BC1. Next is minus N2 by di1 plus N1 by di is equal to N2 minus N1 by dc2. Now, as bi1 is equal to di1, bi1 is equal to di1. Therefore, these two gets cancelled because we can substitute this bi1 is equal to di1. It's n2 by di1 minus n2 by di1. So, when we are adding it, it gets cancelled here. Therefore, we will get that n1 by ob plus n1 by di is equal to n2 minus n1 in brackets multiplied by 1 by bc1 1 by bc1 plus 1 by dc2, and this is the only equation which is even derived here. Okay. So, we got n1 by ob plus n1 by di is equal to n2 minus n1 into 1 by bc1 plus 1 by dc2. Suppose now please look over to the assumption here. We are assuming that the object is at infinity. So, now if object will be at infinity, ob will be infinite. If ob is infinite, n1 by ob will be equal to 0, and similarly value of di will be equal to f. Why it will be equal to f? Because we know that for any refractive surface, if the image is at a higher distance, that is if the rays are coming from infinite, then we can assume first of all that they are para-axial, that is they are parallel to the this principal axis, and after refraction it passes through the focus. So, if it passes through the focus, then the amount of distance, that is image distance, is always equal to small f. Therefore, just substituting each of these values here again. So, basically what you will get is that here n1 by ob will equal to 0, n1 by di will change into n1 by f, which will be equal to again n2 minus n1 into 1 by bc1 plus 1 by dc2. So, as you can see, slowly everything in the Len Makers equation is being formed. Okay. So, this is nothing but your this part, that is n1 by f is equal to n2 minus n1 into 1 by bc1 plus 1 by dc2. Okay. So, this thing has also been explained. Okay, let us move on. So, the point where the image of an object placed at infinity is formed is called as the focus f of the lens, and the distance f gives its focal length. So, basically the definition is being explained here. I will just iterate it again. So, the point where the image of an object placed at infinity, let us suppose it is placed at infinity here. So, it is formed is called as the focus f. So, it is formed right here. So, this is called as the focus f of the lens, and the distance f is called its focal length. Okay. The lens has two foci, f and f dash, on either side of it. So, basically one focus is here, one focus is here. But the sign convention BC1 is plus R1, quite evident, as it is in the same direction of the incidence of light, and DC2. So, DC2 is in this direction, this is minus R2 here. Okay. So, now just substituting the equations here. So, let me just first of all write the equation again. So, it is N1 by F is equal to N2 minus N1 into 1 by BC1 plus 1 by DC2. As you can see, that is N1 by F is equal to N2 minus N1 into 1 by BC1 plus 1 by DC2. Now, you are substituting these things here. So, just substituting these equations here, you will get N1 by F is equal to N2 minus N1 into 1 by BC1 is plus R1 for you plus 1 by DC2, DC2 is minus R2 for you. This is nothing but called as your Len Makers formula. Also, you can do one thing, you can divide the complete equation by n1 here. So, dividing the complete equation by n1 gives you this n1 will change to 1, this will be n2 by n1, this will be n1 by n1. Now, just writing this equation again, you will get 1 by f equal to n2 by n1 is nothing but n21, n2 by n1 will be nothing but n2 by n1 will be nothing but n21 minus 1 into 1 by r1 minus 1 by r2. So, this is nothing but your Len Makers formula. Okay. So, what were the assumptions being used for this equation is, the first assumption is that we are assuming that the sin theta or the angles are very small. If the angles are very small, first of all sin theta is approximately equal to tan theta is approximately equal to theta. So, first of all, when we derived the equation using triangles, then there tan theta was being used, that tan theta was being converted to theta. And the second where it was used was in the Snell's law of refraction, when sin I by sin r was being used, this sin I and sin r was being changed to I and r directly, that there was it was being used. The third is that we are assuming that the image is being at infinity. So, these are the three assumptions which are being used, and finally, we derived the equation which is equal to 1 by f is equal to n to 1 minus 1 into 1 by r 1 minus 1 by r 2. Please remember, please clearly remember, every sign convention is being used very clearly here. So, if you are very strong with the sign convention, the mistakes happening in this lecture or this complete chapter will be very less. Okay. So, let us move on. So, basically this is your Len Makers formula. So, this is nothing but your Len Makers formula. Okay. So, let us move on. So, it is useful to design lenses of desired focal length using surfaces of suitable radii of curvature, quite evident. So, if you have you can try to vary this R1 and R2, and basically you can find out the value of your lenses. So, note that the formula is true for concave lens also. So, basically if the lens is in this form or lens is in this form, it does not matter, the Len Makers formula is valid for both these sequences. Okay. So, in that case, just what will happen is R1 will be negative and R2 will be positive, quite evident, and therefore f is negative, for the previous sequence. For this R2 was positive and f is negative for the initial sequence BC. So, basically R1 was positive and R2 was negative. Okay, let us move on. Now, from the above equations we get n1 by OB plus n1 by DI is equal to n1 by f, quite evident. Again, in a thin approximation, B and D are both close to the optical center of the lens. So, applying the sign convention, now just applying the sign convention simply. So, BO is nothing but minus u. So, this is BO which is minus u in the left hand side direction, DI is your plus V, DI is your plus V. Substituting these values, you will get the answer equal to 1 by V minus 1 by u is equal to 1 by f. This is your nothing but the lens this is your nothing but thin lens formula. So, this equation is the familiar thin lens formula. So, what was the mirror equation? Mirror equation was 1 by V plus 1 by u is equal to 1 by f. What is your lens formula? 1 by V minus 1 by u is equal to 1 by f. So, just remember this, and hence everything is okay. What is your Len Makers formula? 1 by f is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2. So, I think these are only the three equations which you need to remember, and complete chapter is completed. 1 by f is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2. Okay. So, this is your mirror equation. This is your lens equation. This is your Len Makers formula. Okay. So, though we derived it for a real image formed by a convex lens, the formula is valid for both convex as well as concave lenses and for both real and virtual images also. It is worth mentioning that the two foci capital F and capital F dash of a double convex or concave lens are equidistant from the optical center. The focus on the side of the original source of light is called the first focal point, whereas the other is called the second focal point, quite evident. So, you just need to remember which is F and which is F dash. So, basically the focus on the side of the original source of light. So, basically this portion here is called as your first focus, that is capital F, and the other is on the other side. So, basically that is F dash, whereas the other is called the second focal point. Okay. So, let me stop it here only. In the next lecture I will continue discussion from this portion only. So, thank you so much.